preparing for an AI cloud engineering interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like and share, and drop a topic request in the comments. Question 1. How would you design a cloud-native platform for training, deploying, and monitoring AI models? I'd start by separating the ML lifecycle into data ingestion, training, model registry, deployment, and monitoring. On cloud, I usually use object storage for datasets, managed compute or Kubernetes for workloads, and CI/CD to promote models safely. The key is reproducibility. Version data, code, containers, and model artifacts. For production, I'd add auto-scaling, observability, security controls, and rollback paths, because model failures are operational failures, not just data science issues. While answering, focus on the end-to-end ML lifecycle, cloud-native building blocks, reproducibility, automation, security, observability, and how training, deployment, and monitoring connect in a production AI platform. Question 2. How do you choose the right GPU instance type for an AI workload in the cloud? GPU choice starts with workload shape. Training needs throughput, inference needs latency, and cost efficiency. I compare VRAM, tensor cores, interconnects like NVLink, and availability in the target region. For large models, I may use A100, H100 class GPUs. For smaller inference, L4, T4 class GPUs can be cheaper. I also benchmark with realistic batch sizes, because cloud pricing can make a technically faster GPU economically worse. Spot capacity helps when checkpoints are reliable. Make sure to cover workload type, VRAM, GPU generation, interconnects, regional availability, benchmarking, spot instances, and why the cheapest hourly GPU is not always the cheapest solution. Question 3. What is the difference between DevOps and MLOps, and why does it matter for AI cloud engineering? DevOps manages application delivery. MLOps adds data, experiments, models, and drift. In normal software, the code mostly defines behavior. In ML, behavior depends on code, data, features, hyperparameters, and training environment. So I build pipelines that track dataset versions, metrics, lineage, approvals, and model registry state. A strong MLOps setup lets teams reproduce a model, compare candidates, deploy safely, and monitor whether real-world predictions degrade after release. In your answer, talk about how ML adds data versioning, experiment tracking, model registries, drift monitoring, reproducibility, and governance on top of standard DevOps delivery practices. Question 4. How would you deploy a scalable, real-time inference API for a machine learning model? For inference, I design around latency, throughput, and failure isolation. I package the model as a container, expose REST or gRPC, and put it behind an API gateway or load balancer. Auto-scaling should use request rate, CPU-GPU utilization, and a queue depth, not just CPU. I add warm pools to reduce cold starts, cache repeated results where safe, and use canary deployments so a bad model version affects only a small percentage first. Be sure to mention API design, containers, model servers, auto-scaling signals, batching, caching, cold starts, rollout strategies, latency SLAs, and failure isolation for production inference. Question 5. When would you use batch inference instead of real-time inference? Batch inference is best when latency is flexible and throughput or cost matters, like nightly scoring millions of users. Real-time inference fits interactive products where users expect sub-second responses, such as recommendations or fraud checks. I choose based on SLA, freshness, cost, and failure tolerance. Often the best architecture combines both. Batch precomputes candidates or features, while online services personalize or validate decisions at request time. While answering, compare latency, throughput, freshness, cost, user experience orchestration patterns, and examples where batch scoring and online inference work together in real products at scale. Question 6. Why is containerization important for AI workloads in the cloud? Containers make ML deployments portable and repeatable. I pin the runtime, CUDA libraries, Python packages, model server, and application code into one image, then promote that image across environments. This avoids works on my notebook problems and simplifies Kubernetes or managed service deployment. The caution is image size. GPU images can become huge, so I use slim bases, layer caching, vulnerability scanning, and separate model artifacts when updates are frequent. Make sure to cover reproducible environments, dependency pinning, CUDA and driver compatibility, container registries, image scanning, model artifact handling, and deployment portability across cloud services. Question 7. How does Kubernetes help with AI and machine learning workloads? Kubernetes helps standardize training jobs, inference services, scaling, and resource scheduling across cloud infrastructure. For AI workloads, I pay attention to GPU node pools, taints, tolerations, node selectors, persistent volumes, and autoscalers. For inference, I use deployments with readiness probes and horizontal scaling. For training, I prefer jobs or operators that handle retries and distributed workers. The operational trade-off is power versus complexity. Managed platforms can reduce that burden. In your answer, discuss GPU scheduling, node pools, jobs versus deployments, autoscaling, probes, storage, service meshes if relevant, and when managed ML platforms are simpler. Question 8. How would you use infrastructure as code for an AI cloud environment? Infrastructure as code lets me define cloud resources in versioned templates instead of clicking through consoles. For AI platforms, that includes networks, IAM, buckets, registries, GPU node pools, databases, and monitoring resources. The benefit is repeatability. Dev, staging, and production can be built consistently with peer review and automated policy checks. I also separate reusable modules from environment variables, so teams can move fast without weakening governance. Be sure to mention Terraform or similar tools. Version control, repeatable environments, IAM, networks, GPU clusters, policy checks, modular design, and avoiding manual console drift. Question 9. How would you design a reliable data pipeline for training machine learning models in the cloud? For an AI cloud pipeline, I design ingestion, validation, transformation, storage, feature generation, and consumption. Raw data lands in object storage as immutable files. Then processing jobs validate schema, remove bad records, and publish curated datasets or features. I prefer event-driven triggers for freshness and batch orchestration for heavy workloads. The critical piece is lineage. If a model changes, I need to know exactly which data produced it. While answering, focus on ingestion, raw and curated storage, schema validation, transformations, orchestration, feature generation, lineage, data quality, and how pipelines support reliable training runs. Question 10. What is a feature store, and when would you use one? A feature store centralizes reusable ML features with consistent definitions. The big problem it solves is training serving skew. Teams train on one transformation but compute something slightly different online. A good feature store provides offline storage for training, online low-latency serving, versioning, freshness checks, and access control. I still avoid over-engineering. If the team has only one model and simple data, clean pipelines may be enough initially. Make sure to cover offline versus online features, training serving skew, consistency, freshness, feature reuse, access control, and when a feature store may be unnecessary initially. Question 11. What role does a model registry play in production AI systems? I use a model registry as the control point between experimentation and production. It stores model artifacts, metadata, metrics, signatures, lineage, and approval status. Deployment then becomes a controlled promotion, candidate to staging, validation against tests and shadow traffic, then canary or blue-green release. If metrics drop, I roll back to the previous version quickly. This pattern is important because model quality and service reliability must both pass before production. In your answer, talk about artifact storage, metrics, signatures, lineage, approval gates, staging, canary or blue-green deployments, rollback, and separating model validation from service validation. Question 12. How do you secure AI workloads and generative AI applications in the cloud? For AI systems, security spans infrastructure, data, models, and prompts. I start with least privilege IAM, private networking, encryption at rest and in transit, secrets management, and audit logs. Then I protect training data with classification, masking, and access reviews. For generative AI, I add prompt injection defenses, output filtering, and retrieval authorization. The main rule is simple. Never let a model bypass enterprise security boundaries. Be sure to mention least privilege, private networking, encryption, secrets, audit logs, data classification, prompt injection, retrieval permissions, output filtering, and compliance for regulated data. Question 13. What should you monitor after deploying an AI model to production? Production AI monitoring must cover both system health and model behavior. I track latency, errors, saturation, GPU utilization, and cost like any service. Then I add prediction distributions, feature drift, data quality, confidence scores, and business KPIs. Alerts should be tied to action, such as rollback, retraining, or human review. Drift alone is not always failure. I validate whether it hurts outcomes before triggering expensive retraining. While answering, distinguish infrastructure monitoring from model monitoring, including latency, errors, GPU utilization, data quality, feature drift, prediction drift, business KPIs, alerts, and retraining triggers. Question 14. How would you optimize cloud cost for AI training and inference workloads? AI cloud cost optimization starts with measurement. I tag resources, track cost per training run, cost per thousand predictions, and GPU utilization. Then I right-size instances, use Spot for fault-tolerant jobs, schedule shutdowns, cache artifacts, and tune batch sizes. For inference, quantization or distillation can cut compute dramatically. The best engineers optimize cost without blindly hurting latency, accuracy, reliability, or developer productivity. Budgets should be observable. Make sure to cover tagging, cost allocation, GPU utilization, right sizing, spot capacity, scheduling shutdowns, quantization, distillation, batch sizing, caching, and balancing cost with reliability requirements. Question 15. How would you design a Retrieval-Augmented Generation system on the cloud? RAG combines retrieval with generation so the model can answer from current enterprise knowledge instead of only memorized training data. I build ingestion pipelines that chunk documents, create embeddings, store vectors, and enforce metadata permissions. At query time, I retrieve relevant chunks, re-rank if needed, and pass grounded context to the LLM. The hard parts are evaluation, access control, hallucination handling, latency, and keeping indexes fresh. In your answer, discuss document ingestion, chunking, embeddings, vector databases, metadata filtering, retrieval authorization, re-ranking, prompt construction, hallucination mitigation, evaluation, and index freshness in production. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.